Hi everyone, so in this video I'm going to be showing the mechanism for enamine formation. And an enamine is different from an imine because in order to make an imine, like in the last videos, we started with a primary amine. But forming an enamine, we're starting with a secondary amine. And I like to think of this reaction in a kind of a funny way because this reaction low-key sucks. So this reaction is my enemy and I'm forming an enamine, lol. So similar to like in the last reactions in this chapter, this carbon is a solid electrophile right now, but it would be a better electrophile after it grabs a hydrogen from our acidic solution. I know that this solution is acidic because this arrow tells me it's happening, or at least the reaction is being catalyzed by an acid, and acids can't just be existing by themselves. They have to be diluted in some way, and they're normally diluted by water or some sort of alcohol, but we're just going to say water. So that means that water is going to be present in my solution. So I'm going to redraw my carbonyl, but now it's bonded to hydrogen, making my oxygen positively charged. So now this carbon is a super good electrophile, and my nucleophile, the amine, is ready to attack. So one of the lone pairs on my nitrogen is going to come over here, bond to my carbonyl carbon, causing this double bond to break, giving it back a lone pair of electrons. So now I'm going to have an sp3 carbon, where I have my OH. This is my nitrogen with the hydrogen that it already is bonded to, this ethyl group and this methyl group. But my nitrogen is positively charged because it has 4 bonds. And in order to make my nitrogen happy, it has to be deprotonated. So I'm going to take away a hydrogen, and then I'm going to end up with a happy molecule. So I have my nitrogen, ethyl group, and a methyl group. And this is where I formed my hemi molecule. I'm not sure if it's called a hemiamine, but we're just going to say hemi because I'm not sure. So I started with my carbonyl, and I made my hemi, which means that now I have to make my hot electrophile. And if you're unfamiliar with this terminology, I recommend watching my other videos. Free promo, lol. So now that I'm trying to make my hot electrophile, I have to think about what I'm trying to make. So I'm trying to make an enamine, which means I have to form a double bond, but it's not going to be forming a double bond between the carbon and the oxygen because that's what I just broke. I just broke this bond. So that means that I'm trying to get my OH to leave, but I have to give a reason for it to leave. So the way that we try to get things to leave, especially for these reactions, is to protonate them. So I'm going to protonate my oxygen. It's going to grab onto a hydrogen from our solution, probably water, and once it's protonated, it'll have a reason to leave. So I have my OH2, it's positively charged, and my nitrogen stays the same. So now my oxygen has a reason to leave, and my nitrogen is going to kick it out. And it's going to kick it out by using one of its lone pairs to form a double bond. And then this carbon-oxygen bond will break, making water my leaving group. So now I have my CN double bond with the ethyl group, the methyl group. That looks ugly. And my nitrogen is positively charged, and I have water in my solution. This is my hot electrophile. I started with my carbonyl, I made my hemi, and I made my hot electrophile. But this reaction is different from the imine formation reaction because at the imine formation, the nitrogen, the double bonded nitrogen with the carbon, had a hydrogen as a substituent that we could take away to make the nitrogen happy. But now there's no hydrogen that we can take away, but our nitrogen is still unhappy. So we have to find another way to make our nitrogen not have a charge in our final product. And the way that that happens is through kind of like a mini elimination reaction. So even though there are no hydrogens here that we can take off, there are other hydrogens present in this molecule that we can take off to make this nitrogen happy. And the hydrogens that we can take have to be from carbons adjacent to the carbonyl carbon. This is my original carbonyl carbon, and I know that because that's where the nitrogen added onto in this step right here. So since this is my original carbonyl carbon, I know that the only carbons that I can take hydrogens from are here and here. So both of these carbons have hydrogens that we can take. So that means that this one, even though it has 2, and even though this one has 3, we only need to take 1. It doesn't matter which of the hydrogens from the carbons that we take. But since we have 2 options, And these two options will make two different molecules. We have to show both products. Because if I form a double bond here, the molecule will look different than if I form it here, because the left side of the molecule, all of this chunk, has another methyl group coming off of it, while this side of the molecule doesn't. So that means that I'm going to have two products. And after we form these two products, we're going to decide which one is the most stable. So this part is a little bit tricky. I'm going to use different colors. So this is my green carbon, and this is my blue carbon. So let's say I took a hydrogen from my green carbon. How does that work? So something in my solution, probably water, is going to grab a hydrogen from that carbon, which causes these electrons in this bond to fold over and form a double bond here. If a double bond is forming here, that means that this carbon, it can't have two double bonds. It can't have a double bond between this carbon and nitrogen. It can't have a double bond between this carbon and carbon at the same time. So after this double bond is formed by these lone pairs, the lone pairs in this carbon-nitrogen double bond are going to be given back to the nitrogen. So I'm going to draw my new product and explain that one more time. So I have my new double bond here that we just formed, and now my carbon-nitrogen is just a single bond, which does make my nitrogen happy because nitrogen has 5 valence electrons, and in this new molecule it only has 3 bonds, and it has that one lone pair that it really likes to have. And this is the option for the green carbon, taking the hydrogen off of the green carbon. So we're going to do it with the blue one again, and then we're going to see how that product differs from taking it from the green carbon. So if I have a water molecule come in and take a hydrogen from my blue carbon, then these lone pairs will fold over, or this lone pair will fold over and form a double bond, which makes my original carbonyl carbon too crowded. So the lone pairs in the double bond will fold up and give a nitrogen back a lone pair. So now I have a double bond forming on this side instead of on the other side because we used our blue carbon this time. And my carbon-nitrogen bond will be a single bond, and then its substituents will stay the same. But in our answer, both of our nitrogens are happy because we took away one of its bonds pretty much. And this reaction, again, has two different products because there were two different places for us to take a hydrogen away to make our nitrogen happy. So now I have to decide, okay, which molecule is more stable? Well, we know that double bonds, or at least carbons in our double bonds, like to have more non-hydrogen substituents. So if I have a double bond that looks like this, right now it has 4 hydrogen substituents. If it had 1 carbon substituent, then it would be mono-substituted. If it had 2 carbon substituents, it would be di-substituted. You can guess tri-substituted. And this will be tetra-substituted. And a double bond with less hydrogen substituents, aka more carbon substituents, is more stable. So this molecule with its tetra substitution is more stable than the tri substitution, more than the di substitution, more than the mono substitution. So we're going to use that same ideology to apply to our products. So if I'm looking at my green carbon formation molecule, this carbon has 1 carbon substituent, and this carbon has 2 substituents that are not hydrogens. I'm not going to say carbon because there's a nitrogen there, obviously. So that means that this double bond is tri-substituted. And if I'm looking at my blue one, it has 1, 2 non-hydrogen substituents, but it has 2 hydrogen substituents. So that means that my right molecule is di-substituted, making my tri-substituted product more stable. Since this product is more stable, that means that it is my major product. So I'm going to erase my tri, erase my di, and I'm going to put that my green one is major and that my blue one is minor. So we're going to go over the reaction one more time. I'm going to erase this because we don't need it. going to do it one more time. So just like how when we did amine formation, we started with our oxygen grabbing onto a hydrogen, making this carbon a super good electrophile. Our nucleophile, the nitrogen, comes in, attacks a carbonyl carbon, giving our oxygen back another lone pair. So I have a tetra-substituted molecule where my OH stays the same. This is the nucleophile that just added onto it. But I have to make my nitrogen happy. So something in the solution, water, is going to take a hydrogen off, and then I have happy nitrogen and a happy oxygen. But I have to give a reason for my oxygen to leave, so we're going to protonate it. I end up with this molecule where now the nitrogen is going to fold over, form a double bond, kicking off this water. But this step, where I formed my hot electrophile, is different from the amine formation reaction because now there's no hydrogens that I can take off of the nitrogen. However, we can take hydrogens from elsewhere in the molecule, basically doing an elimination reaction where something in our solution, water, is going to take off our hydrogen from the carbons adjacent to the carbonyl carbon, my original carbonyl carbon, which was here, here, you know the deal, here. So I can only take them adjacent from the carbonyl carbon. I cannot take them from carbons adjacent to the nitrogen. No, don't do that, please. So I have two options in this case because this side is an ethyl group and this side is a methyl group. So that'll give me two products. If I use my green carbon to take a hydrogen off, the double bond will form, breaking this double bond, and I'll have a product that looks like this. With my blue carbon, it takes a hydrogen off, the double bond forms, this double bond breaks, and I have a product that looks like this. Then I have to decide which is my major and minor product. And we decided that this one was our major product because our double bond was more substituted than this double bond because this double bond had one hydrogen substituent, 3 non-hydrogen substituents. But this double bond had 2 non-hydrogen substituents and 2 hydrogen substituents. So that makes this one my major product. And we just formed an enamine. And referencing my haha joke at the beginning of the video, this reaction is my enemy, making this product formation an enamine. And this is different from an imine because my product has a single bonded carbon nitrogen, but my amine has a double bonded carbon nitrogen, and that's the difference between these two. So this video was helpful, and let me know if you have any questions.